Welcome to AI Frontiers, where we explore the bleeding edge of artificial intelligence research. Today we're diving into intelligent robotics research frontiers, examining 8 groundbreaking papers from August 23, 2025. These papers showcase robots that learn, adapt, and understand natural language, representing revolutionary advances in manipulation and navigation systems. From underwater exploration to traffic simulation, we're witnessing remarkable breakthroughs that span the entire spectrum of robotics applications. Picture this: a robot delicately folding your favorite shirt, smoothing out every wrinkle with the precision of a master tailor. Or imagine an autonomous car that doesn't just drive safely, but adapts its driving style to match your mood, aggressive when you're running late, gentle when you're enjoying a scenic route. These scenarios showcase underwater navigation systems that function when GPS fails completely, and traffic simulators that actually think like humans. What seemed impossible just a few years ago is now cutting-edge reality emerging from robotics laboratories worldwide. Computer science robotics represents a fundamental evolution beyond traditional mechanical systems. This field sits at the fascinating intersection where artificial intelligence meets physical world interaction capabilities. Unlike conventional robotics that focused primarily on mechanical engineering and basic control systems, modern robotics emphasizes the intelligent software that transforms robots from simple mechanical systems into true cognitive agents. These systems excel at handling uncertainty and real-world chaos, integrating natural language understanding with sophisticated robotic control mechanisms. The 8 papers we're examining today showcase remarkable research breadth across multiple challenging domains. Imagine robotics research as a vast ecosystem, much like a thriving digital rainforest. At the canopy level, high-level reasoning systems enable robots to understand natural language and plan complex action sequences. In the understory, sophisticated perception and sensing systems help robots interpret visual, tactile, and spatial information with remarkable accuracy. At the forest floor, fundamental motion planning and control algorithms handle the precise mechanics of robotic movement. These interconnected layers work together to create autonomous intelligence specifically designed for unpredictable real-world environments where traditional programming approaches would fail. Our first major research theme focuses on advanced motion planning and control systems. Think of this as teaching robots to move through their environments with the grace and efficiency of a skilled dancer navigating a crowded ballroom. We see remarkable breakthroughs in automated parking trajectory planning, where researchers have developed sophisticated mathematical frameworks that ensure planned paths are not only geometrically possible, but also dynamically feasible for real vehicles. This represents the crucial difference between simply drawing paths on paper and actually being able to execute those paths while managing real-world physical constraints. These systems enable robots to move with dancer-like grace and efficiency through complex environments. The second transformative theme involves learning-based manipulation and control systems. This represents a fundamental paradigm shift from robots that follow pre-programmed rules to systems that learn and adapt like students mastering new skills. Consider the groundbreaking research by Cody and colleagues who revolutionized garment manipulation by teaching robots to handle fabric through experience rather than complex mathematical equations. Their LaGarNet system successfully handles unpredictable textile dynamics, representing a breakthrough in deformable object handling. This approach mirrors how humans learn, through practice and experience rather than following rigid instruction sets. The implications extend far beyond textile handling to any manipulation task involving flexible, unpredictable materials. Natural language integration emerges as our third crucial research theme, enabling truly conversational robot control. Imagine being able to talk to your robot the same way you'd give directions to a friend. No programming required, no specialized commands, just natural conversation. Researchers are successfully integrating large language models with robotic control systems, creating machines that understand not just what you're saying, but the contextual meaning behind your words. Multi-head diffusion planners now adapt driving styles based on natural language instructions. When you tell an autonomous vehicle to drive more carefully because it's raining, the system doesn't just process keywords, it understands the contexts and adjusts its entire behavioral strategy accordingly. The research findings emerging from these papers represent genuine breakthroughs that fundamentally advance robotic capabilities. LaGarNet achieves textile handling performance comparable to sophisticated physics simulations while requiring dramatically less computational power. The HDSim framework demonstrates remarkable improvements in safety-critical failure detection, enhancing autonomous driving system testing by an astounding 68%. Dual-reg processing systems achieve 32 times faster data processing speeds while maintaining comparable accuracy levels. Hierarchical AI models now guide robot perception processes, creating more natural and diverse behavioral responses. Multimodal sensing systems create comprehensive environmental understanding by integrating multiple sensory inputs simultaneously. Now, let me take you deep into our paper of the day, a truly revolutionary piece of research that's changing how we think about robot manipulation. LaGarNet, developed by Kadi and colleagues, tackles deformable object manipulation, one of robotics' most notorious challenges. This research represents a quantum leap in solving problems that have puzzled robotics researchers for decades. The system employs goal-conditioned recurrent state space models that learn fabric behavior through direct experience rather than attempting to model complex textile physics mathematically. The challenge involves handling materials with infinite degrees of freedom, where every tiny fabric section can move independently, creating an almost impossibly complex system to model using traditional approaches. LaGarNet's technical innovation lies in its sophisticated architecture, combining memory, goals, and hybrid learning approaches. The recurrent structure maintains manipulation memory, keeping track of previous fabric interactions and how they inform future decisions. Goal conditioning mechanisms plan systematically toward desired garment configurations rather than random manipulation attempts. The hybrid training methodology combines random exploration with human demonstrations, ensuring both breadth of experience and proven effective techniques. Coverage and alignment reward functions guide the learning process toward behaviors that effectively flatten garments while maintaining proper orientation. This approach achieves dramatically reduced computational requirements compared to traditional physics-based modeling approaches. The impact and applications of LaGarNet extend far beyond laundry folding capabilities. The system demonstrates success across 4 different garment types in both simulation and real-world settings. This breakthrough opens remarkable possibilities for surgical suturing robots that could learn to handle soft biological tissues. Manufacturing systems could handle flexible materials like rubber or leather without extensive reprogramming. Food preparation applications could include robots learning to knead dough or shape pastry with human-like intuition. The methodology provides a comprehensive template for learning-based manipulation approaches across countless domains involving unpredictable, deformable materials. This represents a fundamental shift from requiring teams of physics experts to systems that learn through experience and practice. Looking toward the future, these research directions point toward a robotics landscape that's more adaptable, intelligent, and integrated into human society than ever before. Think of the current state as standing at the edge of a vast ocean of possibilities, with today's techniques serving as the first ships setting sail toward new continents of capability. Natural conversation-based human-robot collaboration will become as seamless as talking with friends. Multimodal perception systems will create rich environmental understanding that rivals human sensory processing. Manufacturing systems will adapt to new products without reprogramming, learning to handle novel materials through experience. Healthcare robots will develop increasingly sophisticated capabilities for delicate procedures. No environment will remain off-limits to robotic exploration and operation. Today, we've journeyed through a landscape of robotics research that's fundamentally reshaping our understanding of machine capabilities. We've explored robots learning to handle fabric with human-like intuition, autonomous vehicles adapting their personality to match user preferences, and simulation systems that think like humans. These systems represent robots moving from simple execution to true understanding, developing learning, reasoning, and human collaboration capabilities that transform manufacturing, healthcare, transportation, and countless other domains. Most importantly, this research makes advanced robotics accessible to everyone, removing technical barriers through natural language interfaces and adaptive learning systems. The future we're witnessing isn't something that happens to us. It's something we're actively creating through brilliant research and thoughtful technology application. This synthesis was created using GPT Anthropic Claude Sonnet 4 2025-05-14 with TTS synthesis powered by DeepGram technology and image generation enhanced through OpenAI systems. The content has been reviewed by human robotics experts to ensure accuracy and relevance. While we strive for complete accuracy, some oversights may exist, and all original research references are provided for your further exploration. We encourage you to dive deeper into these papers yourself, as each represents months or years of brilliant research that we've only been able to touch on today. Subscribe to AI Frontiers for cutting-edge research analysis and weekly deep dives into breakthrough papers. Join our expert analysis of artificial intelligence advances and participate in community discussions about our robotic future. Your voice matters in shaping how these technologies develop and integrate into society. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archivepreprinserver.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archivepreprinserver.org.